So we're on to the strength calculations now. Right, so we have the beam and we identify that we say L is equal to 0.6 meters. Right, so we have these distances here now. Right, so we need to now have a numbering system for the beam. So we're going to identify and pull out each beam and we're going to do the analysis on it. And by analysis, we're going to do bending moment diagram, bending moment, shear force, then we're going to obtain the bending stress, the shear stress, then we're going to get the maximum shear stress, and then compare that to your sigma yield. That's what you would have done. You would have known these terms from when you did strengths of materials. So to number the beams, you're going to say the top here is beam number 1. This vertical one here is 2. The bottom here, we say that is beam 3. And one side here, this beam here is 4. Right? There's no need to do this beam and this beam because it's symmetrical. So you do beam 1, and essentially that means you do this beam. You do beam 4, and essentially you also do this beam. So those are the beams we're going to look at. I'm going to look at each individual beam. You're going to draw the bending moment shear force diagram. From that, obtain the bending stress, the shear stress, and then we're going to combine the loading to get tau max, or your maximum shear stress. And then we're going to compare this sigma yield on 2n by n is a factor of safety and see if it's safe or not. Right, so let's begin with beam 1. So beam 1, what we are assuming here is that we said that from the design requirements, it must be able to transport 45 kilograms, which is around 45 or 450 newtons. Right, so we are assuming here now that, of course, we can't say all the load is at one end. That doesn't make sense. We won't put 45 kilograms on this one end. So, but what we could assume to be safe is that the load is being hung throughout the length of one side. So normally you would have some here and then some here, but in this case we are assuming that all the 45 kg, they put it on one end here. So we have baskets, we have loads. So what we essentially end up here is a cantilever beam with a uniformly distributed load. So for beam 1, what we have, a cantilever beam, right, with a uniformly distributed load. So the length is 0.5 meters. And now we need to know what is this UDL load. So we said that's 45 or 450 newtons distributed over 0.5 meters. So that really is 900 newton per meter. So the distributed load here is 900 newton per meter. So now we could go ahead and draw the shear force and bending moment diagram. Right, so now you would understand why we emphasize so much in strength the shear force and bending moment diagrams, because it's the fundamental process of doing strength calculations. So the shear force would be, let's say this would be shear force here, this would be bending moment. So the value would be 450 and the bending moment diagram would be minus 113 Newton meters. Right, so I'm not going to show how we came up with the shear force and bending moment diagram. So that will be an exercise you can do. So that would be an exercise. Obtain obtain the shear force and bending moment diagrams. Right, just like any assignment, and also identify the maximum. So you're gonna identify the max values because we would use those max values now in determining the shear stress and bending stress. So we could go ahead now and calculate the shear force, which is 413 V on A. Right, so this would be 450 over the area, and the bending stress would be a maximum bending moment, which in this case is minus 13. Alright, so this is minus 13 Y on I. So you could recall getting your bending stress from strengths, where Y is the distance from the neutral axis and I is the second moment of area. Right, so we said that we are using a pipe section. So a pipe section, so this would be a neutral axis. The maximum stress would be on the outskirts of the pipe itself. So simply enough, that would just be your radius. Before moving on, I just want to let's come back to something here. These terms here, right? This term, this 413 VA. Not sure if you did it in strengths, but for a circular cross section, right? The shear stress, so the shear stress, the force being acted upon it is V. The maximum shear stress that is experienced over the cross section is 413 V on A. Right? Because the shear stress across the cross section changes as you go through different layers in the cross section. But the maximum is 413. For a square or rectangular cross section, the maximum would be 312 V on A. So these are just two things to keep in mind as we go along in the course. Right? Because we'll be mostly or all the time looking at either square sections or round sections. Just keep things simple. Right? The pipe section in question, we say that this has an outer radius of R2 and inner radius of R1. That's a shaded region here is the solid region. We say that the area will be pi right, the second moment of area I will be pi into R24 minus R14 over 4. So this is I. So this is how we would calculate the I term and the area term. Right, these values of R2 and R1, we would obtain this from actual pipe data. Right, so we go online and get a data sheet or something as to what are these R2, R1 based on the pipe diameter. Right, so the thinking is now is that we keep everything parametrically and we're using up something like Excel, and as we go along we keep changing the radius. We change R2, we change R1 until we get the stress to be where we want it to be. We write down all our stresses. We have tau xy, Again, I'll just put back in everything here. V on A, I'll say V max. Our sigma bending is really our sigma x, because you could recall the bending stress acts in the direction, in the x direction. When if you were to bend a beam or you bend a ruler, for example, what you're really doing is stretching the top surface and compressing the bottom surface. So that in order to stretch and compress, you need to apply a force in that direction, or apply a stress, I should say, in that direction. So our bending stress is really sigma x, and we said that's our M max Y on I, right? Where I was our 2 on 2, and we have I from over here. The next piece of the puzzle here is sigma Y. And sigma Y is 0 because if you look at a stress element from the beam, so let's just say, let's just pull out a stress element from the beam. This is the beam here. We're looking at this region here, so I want to zoom in on that. Right, we have the shear stress. This is our V. And you have now our bending stress, our bending moments like this, which causes the bending stress. Right, so there is no stress in the y direction. We have our bending stress, our sigma x, which we say acts in this direction. And we have our tau xy, sorry about that. We have our tau xy stress. But there's no sigma y. So therefore we could say now that sigma y is 0. So we have tau xy, sigma x, sigma y. So the next thing we're looking at here now is combining stress states. And you will have done this in strengths when you did Mohr circle. So this formula, tau xy, or tau max I should say, not tau xy, is equal to a half right? So you could recall this formula, which was the radius of your Mohr circle. Right, so this tau max here, when we come to doing, when we start doing failure theories, you will understand this a little more. But for now, T max represents the combined state of stress. Is a representation, a combined state of stress. In the solid. So we could actually compare this now to something. Now, recall in strengths, we had stress versus strain, and when in the laboratory they would have done this, the stress strain graph, we said that the gradient here is E, which is your modulus of elasticity. And we said that at this point over here, this was our elastic limit. Right? If it were to stretch beyond this, then what will happen is that the material will return back onto a different line. If we were to apply stress to this region here, and we remove the load, the material will return back to its original configuration. If we were to stretch up to this point, it will return back if we load. But if we were to go beyond this point here, and say we pull the material up to here, we apply that amount of stress. Then when we release the stress from it, it will actually shrink back down or come back down to this portion, meaning that now the material is permanently deformed. Kind of like if you overstretch a rubber band. So this point here, we call that our yield point, or elastic limit. So that is sigma yield. Or you would say, I would write sigma yield point, YP. And what we're saying is that we don't want the state of stress in the material to surpass this. Because if it surpasses this, then you would have permanent deformation happening. So now we have a material property that we could compare to our calculated stress. So if you recall, again, from strengths, we had a solid bar, we had applied a load P, and we would stretch this bar. So this here is your tensile test, right? And in doing this, we apply a stress sigma x is equal to P on E. So we apply that stress, and we end up with the same stress strain graph, right? Now, in this situation here, the combined state of stress is what? Sigma x is P on A, tau xy is 0 because there's no shear stress, we're just pulling this axially, and sigma y is 0. So therefore, from this, our combined state of stress, in this case, in the tensile stress I should say, is the square root of sigma x, sigma y is 0, so this will be squared, plus 4 tau xy, and well, tau xy is 0, so we could remove this, and there's a half in front of here, which is really sigma x on 2. So in a tensile test, the tau, how to say, at the yield point is really a sigma yield point on 2. So now we could compare tau max for the beam to the tau yp for the material, right? So we know if we cross this tau yp, we enter in problems, permanent deformation, all that, so we want it less. So we actually want tau max for the beam to be less than our so-called sigma yp on 2, right? So this is our shear stress failure theory, right? And we will do this in more detail, or if we haven't done it already. I'm not sure where we are at in when it is you're viewing this video. Right, but instead of being too exact, what we include now, they call a factor of safety. And this also is another lecture as to how we select a factor of safety. So we include a factor of safety n. Right, so what that means is that we over-design by a certain factor n. So if the sigma yield, if this yield point is say 100, we say, okay, let us not push it to 100, let us push it to 50. So what that means is that the safety factor is equal to 2. Right, so we say tau max should be less than sigma yp on 2n. So this is our failure theory. Our sigma yp, again, this is our yield stress, and we will obtain this from tables and charts and stuff like from MathWeb, for example. You go online there and you get the sigma u. 2n, this is our factor of safety, and this depends on this will depend on the type of loading, for example. So standard we use 2, so it's usually about 2. But depending on if it's a dynamic loading, for example, if it is people are throwing tools on this basket as opposed to resting it down, then we could go up to about 4. So there are tables and charts again that I will cover in a lecture that govern this. So now we have our tau max calculated here. We could compare it to the actual material property. And if that tau max is less than this value, then we could say it's safe and we can move on to the next beam. Right, so everything is in terms of parameters right now, but as we saw here, we have value for V, we have a value for M. We could calculate A, we could calculate I, we could calculate Y. That means we could calculate sigma B, which is your sigma X. We could calculate tau XY. We know sigma Y is 0. So as we calculate all those things, we could substitute here and calculate tau max. Right, the reason I'm not doing it now is if you put in all those figures now, the video will be ridiculously too long and boring. Right, so what I'll do in the end, I'll put everything on an Excel sheet, and you could actually put in the values for yourself and compare it and calculate and see if it's coming back. It will be a nice exercise to get accustomed to working with these types of equations and these types of figures. Because in the beginning, you will make mistake in having r to the power of 4, the square root signs, all these things it takes some time to get accustomed to. Right, so now we're going to look at beam 2. So with beam 1, we had the load being applied like this, right? And as a result, we saw in the shear force bending moment diagram, we had a reaction force and a reaction moment. Right, so if we were to look now at the joining between beam 1 and beam 2, we could draw a free body diagram like this. We have the beam 1, we have the load. Right, so this is beam 1 here. So we have a reaction force, and that reaction force was 450 newtons. And then we had a reaction moment, which we determined from the shear force diagram to be 113. So 113 Newton meter. Now if we look at beam 2 now, which is vertical, that reaction force, first one opposite and equal to, this is 450, and the opposite and equal to moment will be in this case clockwise like this. And that will be 113 Newton meter. So this here is beam 2. We also have the pushing force, FP, because remember that's where we're pushing. And we said that was equal to mu well 2 mu by the friction force. Right, so we could show by calculation that will be equal to 0.04 by 450, which is 80 newtons. So this is the FP. Right, so dimension wise, length of our beam is 1.8 meters. Just recall that there, right? And we said that the pushing force was at 1 meter from the base. So this is our beam, but it's vertical. So what we can do to make life easy, we could just rotate the beam because we have all the forces on the beam. So we could rotate it. And now we have 18 newtons. We have a force in the axial direction of 450 newtons. And we have a moment applied to the end of 113 Newton meter. And our length 1.8, and then this is 1 meter. So that is our beam. So we could go ahead and draw our shear force and bending moment diagram. Again, this will be an exercise for you to complete. Get this line here, and then another line here. So the purpose of these lines is just to Okay, so our shear force diagram would look like this. So this is V newtons, this is 18, and our shear force diagram Right, so this is our bending moment and shear force diagram. Yeah, so as an exercise, you could draw the shear force and bending moment diagram and ensure that you get the same values that we got here. Right, so our Vmax is 18 newtons and our Mmax is 131 Newton meters. Right, so we have the negative sign here, but the negative sign would mean that as the beam is bending, right, so this is the beam here, as it's bending down, it will be, the bottom will be in compression, the top will be in extension. Right, so in this case now it is important that we try and visualize that. So I'll talk a bit about that now. If we have a beam and the beam is bending, so let's exaggerate how the beam is bending here, right? Because we have some force over here. In order for the beam to bend and curve, in order to get that curvature, it means that this distance from here to here, that distance there, S top I should say, because it's the top, is actually greater than this curved distance here, S bottom. Right, so this distance on top here is greater than this distance at the distance below here. So that means the fibers on top are stretching, whereas the fibers below are compressing. Right, so let's suppose this is really supposed to be a recap of strengths of materials. So if we look at the cross section of the beam, we see that this is what we call the neutral axis. So the fibers on top here, this is coming out of the page, will be in tension by a value of sigma x, which is really sigma bending. And the fibers here below will be in compression. Right, and the value of compression at compression x is also compression sigma x is also sigma bending. So the top again be stretching, the bottom here will be compressing. So in our case, if we go back to the beam, there's this force here, 450 Newton, that is compressing the beam. Right? So let's take this over here. So we don't have to be going back and forth. Right, so we see that the top, these are the different colors, the top is under tension, and the bottom here is under compression. Now remember we have an axial force of 450 that is compressing the beam also. So your bending stress on top, so our bending stress on top here, sigma will be sigma bending minus 450 over area. Because remember, your compressor stress is force over area. And the stress below here, right? So this is your stress on top. The stress below here will be minus sigma bending because it's compression. Again, minus 450 over A. Right, so this here is on top, and this stress here is at the bottom. Right, so we sum these stresses. So what we did here, we sum these stresses in the axial direction. So out of these two values, which one you think will give you a larger value? Forget that if it is negative or positive. The larger value would therefore be sigma x. Maximum value would be this actual value here, which is right. So our sigma x, therefore, that we will use in our calculation for tau max calculation would be m max y on I minus 450 over A. So this would be our sigma x. Our tau xy, we said before, is 4 on 3 by V max over the area. And our sigma y, we said, is 0. So we could go ahead and say tau max is equal to a half right? And then we ensure that our tau max here is less than sigma yield on 2n. So that is how we determine now for beam 2 our tau max value. Right, so we draw a free body diagram of the two beams in connection. So it'll be equal and opposite. The forces applying to each side or each part of the joint. Then we rotate the beam such that in a form that is familiar for us. So in this case, we are accustomed drawing the beam horizontal like this. So we draw it like this. And then we draw our shear force diagram, bending moment diagram. We pull out from the diagrams our max values. And then now, at this stage now, we need some reasoning to figure out, well, how does 450 Newton force coming into play? And that is what we have shown here. There's a compressor force that will actually balance out some of the stress on top, but increase the compressor stress on the bottom. Right, so the larger of the value would be the stress at the bottom, which is in the blue. Our sigma bending is our bending moment by yi on I, and subtract that from your compressor stress here. So that will be our sigma x, tau xy, sigma y, and then we could get our tau max. So you could see more or less we're kind of repeating the same values. The y is the same, I is the same, area is the same. Sigma y is the same, well that is 0. Sigma yield on 2n will always be the same. So what we could do now is set up an Excel sheet to do these calculations, to simplify life. Right, so now what I'll do, I'll go on to beam 3, which is the bottom beam here. Right, so we're looking at beam 3, and we say that to analyze a present beam, we need to go back to the beam before to get the reactions. So in this case, we're looking at going back to beam 2 to get the reactions. Right, so if we go back to beam 2, we could see here that the reaction force was 18 and the reaction moment was 131. Right, so I'll just bring this across here so that we'll have something to look at. Right, so we don't need the applied forces and all that. We just need the reaction forces. So it was 18 and 131. Right? We also had a reaction force of 450 to counteract this force here. So these were our reaction forces. Now remember we had turned the beam horizontal. So if we rotate back the beam vertical to match the diagram, this is what we would have. Right? So if you were to sketch out our beam 3 now, this is our beam 3. This is where it connects to beam 4. Right? Our distances are 0.6 meters. Our reaction forces, therefore, is equal and opposite. So we have the 450, which balances out this force here. We have a force in the equal and opposite direction of 80 newtons. It balances out this force here. And then our reaction moment, here it was anti-clockwise, so therefore here it will be clockwise, which is 131 Newton meter. So this is our loading on beam 3. Right, so in this case now we have two sets of forces in two different planes that is acting on one single point in beam 3. So to make life easier, we could find the resultant force of the 18 and 450 Newton forces. So you can recall how to get a resultant force. Right, so basically you have 450, you have the 18. So what we're doing is getting this force here. No, wrong, to that wrong side. 450, 18. So the force will act like this. So this here is your resultant force. Right, so this resultant force will be equal to, if you really were to work this out, 18 squared you would approximately get back 450. In my case, I'm getting 450.4, which is, we could round it off to 450. So you almost get back the same vertical force. That is because the 18 is so small. The pushing force is so small that the real loading on this beam is from the load of the tools and not so much the pushing force of the person who is pushing the cart. So we could simplify the beam to be as simply supported, where we have a force at the center of 450 newtons, and we also have a torsion. So included over here is a torsion of 131 Newton meter. Now if the torsion was in this direction, then it would be applied as a bending moment, and it would be part of the bending moment diagram. But in this case, is not. It actually is in the plane of the paper. Right, so if we were to go back in this diagram here, the torsion is being applied in this way, causing it to spin. So you're actually trying to spin beam 3, as opposed to how it was previously over here. So that is what we have to deal with now. So we have beam 3, which is loaded at the center, and then we have a torsion of 131 Newton meter that is trying to twist the beam. So let's twist now the beam. Let's talk more about it. We said that the cross section of the beam is a pipe. Right, so this is the pipe. Right, so somewhere along here we have 450. I'm gonna draw the whole thing just to completion sake. Right, so somewhere in the middle here we have the 450 Newton being applied. Right, this is the center line of the pipe going through here. So what we have is twisting of this pipe by 131 Newton meter. Right, so the pipe is fixed. By fixed, I mean it is allowed to be simply supported, but is not allowed to rotate. So the pipe is not allowed to rotate. Right, so essentially what we have there is torsion. So this demonstrates now two types of loading. That is, we have a beam point load, which we could handle, and then we have a torsion load. So to analyze this, we look at the beam point load and we go through our normal method, shear force diagram, calculate shear stress, bending stress. Then we look at the torsion load and we work out the torsional shear stress, which you could recall from strengths when you did torsion and circular cross sections. Right, so we'll tackle the beam first, and the beam is it's I think as simple, the simplest as it could possibly get. Right, so the shear force bending moment diagram. Let's construct. Right, so again, this will be your exercise. Mm. So this is V newtons. This value would be and the bending moment. This value would be 135. Right. Again, our reaction forces would be 450 divided by 2, which is a shear force in this case. So our sigma bending, which is sigma x, will be our M max y on I. Our M max in this case is 135. And now we come to our shear force and our shear stress. So the maximum shear stress is 225. And in the past we have seen that tau xy was 413 V max on A. So this is still correct if we only look at shear stress due to the point load alone. Remember now we have torsion. So the torsional shear stress must also be now considered. And if we could recall the formula for torsional shear stress, tau xy, I put torsion in below here just to separate, is equal to your torque by, in our case, R2 over G. And G is your polar moment of inertia. T is your torsion, and R2 is the distance to the outermost fiber. Right, so calculation of J, this value you could get from the internet or back of the textbook. I would have also, it was supposed to be in your strengths notes also. J is half of your value of I. So we pi on 2, R24 minus R14. So that is your J. So we could say now our tau xy, or our total tau xy, is really 413 V max on A plus your tau xy from torsion, which is TR2 on G. So this would be our total tau xy that has been applied to the beam. Right, so let's go over that again. We said that the pipe or the beam is having a torsion in the axial direction. So that's this direction. Right? If you want to ask why, it's because that is just how the loading was. We had the vertical beam, and if you were to push on this beam here, the beam would want to rotate. And because it being attached to this member beam tree, it will want to twist the beam or twist member tree or beam tree. So that is a torsion, and the value of that torsion, we worked it out to be 131. So we have a point load on the pipe, on the beam, on beam tree, whatever it is we want to call it, and that will give us a shear force, and that shear force is 225, or maximum shear force 225 newtons, and this shear force will give us a shear stress, which is we are accustomed to calculating that by now. But because of the torsion, we now have to factor in this torsion. So we have a torsional shear stress. So that torsional shear stress formula is just a recap of strengths, is given by a torsion R by R2 over J. J is the polar moment of inertia. Right, so in our case here, our T value would be 131 Newton meter. Our V is 225 newtons. So this calculation will give us our tau xy. So again, here we calculated sigma x, which is sigma bending. We have our tau xy. we know sigma y is equal to 0, we could get tau max. Right? And then we ensure that tau max is less than sigma yield on 2n. So now we could go on to beam 4. Okay, so we're going to look at beam 4. Now, as previous methods, we're going to go back to beam 3 and see the forces, the reaction forces from beam 3, and then we'll apply that to beam 4. So if we could recall, this was beam 3. We had a force here, a reaction force of 225 on either end. And also we had, in this plane here, we had a torque that was being applied. And this torque was 131, I think it was Newton meter. So newtons. Right, so just to recap that here. Right, so in actual it was this was the okay, right. So this was the reaction torque from beam 3. So we have this expanded. We have beam 3. We have the reaction forces on beam 3. 225, 225. So therefore on beam 4 is like this direction. The forces therefore on beam 4 will be equal and opposite. So it will be the font color. Two two five, and the moment will be equal and opposite to this. So it will actually look like this. 131 meter. So this is beam 4. Right, and it's on rollers, so we're saying it's simply supported. So this is the actual beam here. This in perspective, this is beam 3 over here. This is beam 2, and so forth. Right, so this is actually beam 4, and if you were to include the dimensions, it would be 0.6 meters, 0.6 meters. So now we could actually isolate beam 4, draw it horizontally. Have our reaction forces, and we also have a moment at the center here being applied 131. Okay, so I've jumped ahead to the shear force and bending moment, and I already worked it out. So this will be the shear force and bending moment diagrams for this particular system. Again, that's an exercise for you to do. If you notice, the shear force diagram is not symmetrical, even though the distance between the two between the middle and the forces there is equidistant, 0.6 meters, and that is because we have this moment being a part of the system now. So you have to consider that moment when finding the reaction forces at either ends. So that is why the shear force diagram looks like that. And the bending moment diagram, because we have an applied moment, then it will be represented as a jump in the graph. Okay, so now that we have the shear force and bending moment diagram, we could go ahead and, just like before, work out our three planar stresses. Planar stresses meaning the x, y directions. So sigma x is sigma bending, which is M max Y on I. Sigma Y is equal to 0. And tau xy, again we said is 4 on 3 V max on A. Right, so if we go back to our diagram, M max equal to 133, V max is equal to 222 newtons. So now that we have our planar stresses, then we could combine the tau max equation, and then we take that tau max equation and we compare it to our sigma yield on 2n. And that will be it. We keep manipulating the property sections. Again, we keep changing R1, R2. So when R1 and R2 changes, right, so if R1 and R2 changes, that means A changes. Also, I changes. So if A changes and I changes, you could see from these two equations that the sigma x and your tau xy changes, which would mean our tau max would change. So this is where we use Excel so that we could create a table. We have R1, we have R2, we calculate A, we calculate I, we calculate J because we had used J for beam 3, calculate tau xy, calculate sigma x, and we get tau max. So in Excel, we have all these being changed so that as we are changing R1 and R2, we could see the effect on tau max because this is what we are comparing to what we call tau design. Right? Tau design is our design stress is what we want to achieve, or we want to build, keep it below. And let's reiterate the sigma yield on 2n. Right, so that's one way of doing it, is where we use Excel and we keep changing these values. Another way is to specify a value. So that is, we could say, for example, we say we want to use a 1-inch schedule 40 pipe. So what that means is that we have R1 and R2 from some table that details the pipe. And then we plug this now into all our equations that we had before. And if we say that if the tau designs, if our tau maxes are less than tau design for all beams, then we say it's good. We could use the 1-inch schedule 40 pipe. So that is the design exercise, and I don't want to say a nutshell. It's a big shell, but this is the calculation that is expected from design project 1. Right, it looks like a lot, but if you notice, it's the same thing that's being repeated over and over and over. The hardest part is to identify the arrangements of the forces. So these arrangements, how we have the torsion, how we have that force, how it is connected to beam 2, in the case of beam 3 to 2, 3 to 4. So that is the difficult part. That is the critical thinking. That is what you'll have to learn. The formulas to any shear force and bending moment diagram, that is a repetitive process. And we have seen now with the actual calculations, we could automate in Excel. So you put in the parametric equations once in these cells, you drag it down, and you keep changing your arrow on that too.